All right, today we're putting on our coach's hat and opening up the playbook on how to train a really powerful neural network. Let's get right into it. So, here's a fun one for you. On one hand, you've got a star athlete, the peak of human physical performance. And on the other, a powerful AI, the absolute cutting edge of technology. They seem like they're from totally different worlds, right? But what if I told you they share a fundamental secret to success? Yup, that's it. Coaching. An AI, just like an athlete, doesn't just wake up one day and become amazing. No way. It needs guidance. It needs a solid set of rules and a really smart training plan to unlock its full potential. And today, we're going to be that coach. Okay, first things first, let's really understand the challenge we're up against. The single biggest problem a coach has to help their AI overcome is this tricky little thing called overfitting. So, what is overfitting? Well, imagine a student who crams for a test. They memorize every single answer on the practice sheet and they get a perfect score. But then you give them a new problem that's just slightly different and they completely freeze up. They didn't actually learn the material, they just memorized the answers. That is exactly what an overfit AI does. And our job as the coach is to make sure that doesn't happen. So, how do we do that? Well, we start with the fundamentals. In the world of AI, this is called regularization. You can think of it as teaching our athlete the basic rules of the game before they even start thinking about the fancy advanced plays. Our first technique is something called dropout. And I know, it sounds a little weird, right? Why on earth would we want to randomly turn off parts of our AI's brain while it's trying to learn something? Well, think about a basketball team. If you have one superstar player who always makes the winning shot, the rest of the team never really learns how to step up. But what if during practice you randomly make that star player sit out? Well, everyone else is forced to get better, to learn how to score on their own. Dropout does the exact same thing for our AI. It forces the whole network to become more resilient and less dependent on any single star neuron. Next up, we have weight decay. This one is all about encouraging simplicity and elegance. See, an AI can create these incredibly complicated connections to solve a problem, but those super complex solutions are often a one-way ticket to overfitting. Weight decay adds a tiny penalty for all that complexity, nudging the AI to find the simplest, most efficient answer instead. Here's a great way to think about it. Imagine you're packing for a trip, but the airline charges a massive fee for heavy luggage. What do? You learn to pack light, right? You only bring the essentials. Weight decay is that fee. By making complex connections costly, the AI naturally learns to pack light, keeping its internal model lean and effective. And that helps it generalize way better on new problems. Now for what is, honestly, one of the cleverest tricks in the entire playbook: data augmentation. What do you do when you don't have enough examples to train your AI? Simple. You just make more. This is all about teaching the AI to recognize something no matter how it might look out in the real world. So let's say we're training an AI to recognize cats. We don't want it to only recognize a cat that's sitting perfectly still, facing forward. So we show it that same cat picture but flipped horizontally, rotate it a little bit. Maybe we mess with the brightness or zoom in. By doing this, we teach it a crucial lesson. A cat is still a cat, even if it's upside down or in bad lighting. Okay, so our AI knows the basic rules. It's got a good foundation. Now it's time to start fine-tuning its training regimen. This is where we, the coaches, start adjusting all the little dials of the learning process. These are called hyperparameters, and they're all about finding the perfect learning style for our AI. First up is the learning rate. You can think of this as the size of the steps the AI takes as it gets closer to a solution. At the beginning, you want it to take big, confident strides to cover a lot of ground fast. But as it gets closer and closer to the best answer, you want it to take smaller, more careful steps to really zero in on that perfect spot. That's what a learning rate schedule lets us do. Next, we've got to decide how many examples our AI should look at before it updates what it's learned. This is called the batch size, and it's a classic trade-off. Using small batches is kind of like one-on-one tutoring. It's slow, but it can lead to a really deep understanding. Large batches, on the other hand, are like a huge university lecture. It's way faster, but it's easier to miss some of the finer details. And finally, we have to think about the actual architecture of the AI. Do we build it deep, with lots and lots of layers, so it can learn really complex, abstract patterns? Or do we build it wide, with tons of neurons in each layer, so it can memorize more details? There's no single right answer here. It really depends on the problem you're trying to solve. We've built a solid foundation, and we've fine-tuned the regimen. Now it's time for the advanced coaching techniques. This is all about making sure our AI not only finds an amazing solution, but that it gets there efficiently and without any catastrophic failures along the way. One of the biggest fears for any AI coach during training is the exploding gradient. Gradients are basically the signals the AI uses to learn and get better. But sometimes these signals can get amplified and become so ridiculously massive that the whole training process just becomes unstable and breaks. It's pretty much the AI equivalent of a total meltdown. But thankfully, there is a simple and really elegant fix for this: gradient clipping. We just set a speed limit. If that learning signal starts to get way too powerful, we just clip it. We trim it back down to a level we can actually manage. This stops the training from ever spiraling out of control. Now, here's another issue. Sometimes our AI can get stuck in what's called a local minimum, a solution that looks pretty good, but it's not actually the best possible one. It's like thinking you've reached the top of a mountain, but you're actually just in a small valley, and the real peak is over the next hill. Warm restarts are how we fix that. By periodically resetting the learning rate to a high value again, we give the AI a little jolt that helps it jump out of those valleys and continue searching for an even better solution. And finally, let's talk about a real pro-level optimization trick. Mixed precision training can dramatically speed up the whole process and save a ton of computer memory. It works by doing most of the math with less precise numbers, which is way faster, while strategically keeping the most critical calculations at full precision. You really get the best of both worlds: incredible speed and rock-solid accuracy. So, after all of that coaching, where does it leave us? Well, through this whole process, we've taken our AI and transformed it from a complete, untrained novice into a robust expert, one that's capable of taking what it's learned and applying it to solve new problems it has never seen before. So there it is, the complete coach's toolkit. We taught its fundamental rules with regularization, we broadened its horizons with data augmentation, we dialed in its personal learning style with hyperparameter tuning, and we made sure it had a stable, strong finish with some clever convergence tricks. We've done it. We've successfully coached our AI to be incredibly effective at its job. It's a champion. But this entire journey leaves us with a much bigger and honestly more profound question to think about. We've figured out how to make an AI perform well, but what's it going to take to teach it the wisdom that should go along with all that power? Thanks for joining me.